Hey guys, so in our last video, we looked at how Thevenin's and Norton's theorem works, and we also solved a problem that enabled us to better understand how to find the equivalent resistance and why using Thevenin's theorems makes our lives so much easier. So in this video, I have another problem for you guys, and this time we're going to use Norton's theorem or a Norton circuit. We're going to convert it to a Norton circuit. So if you remember, Thevenin's circuit has a voltage source in series with a resistance, and the Norton circuit has a current source in parallel with a resistance. So I'm gonna convert whatever is in the red box to where I get this circuit. This is going to be my load. So this is my load resistance, 1.5 ohms. It's going to be my Norton's resistance, Norton's current. Right? So in this problem, we got to find what is our Norton's current, what is our Norton's resistance. Remember, we're just simplifying what is in the red box. So whatever is in the red box is equivalent. Alright, so let's go ahead and find our Norton's current. So if you remember, in finding the Thevenin's voltage, the first step was to remove the load resistor, right? So we're going to do the same thing in our finding the Norton's circuit. But this time, we're going to remove the load resistor and we're going to short it, right? Alright, that was really messy. Let me redo that. Right? So we're going to short it. And we're going to find what is the current that is flowing here. So this is going to be our short circuit current. So that is going to be your Norton's current. So if you remove the load and if you shorted those two terminals, what is the current that's going to flow there? So this is known as short circuit current. And if you look at it, this circuit diagram right here, I've removed my load, which was here, and I've shorted these two terminals. So the short circuit current is the same current that would flow across the 3 ohm resistor. Right? So we would have one current going this way, and we would have another current branching out. So it would branch out at this junction right here. So we're going to find the current that I've denoted in the yellow. So to do that, we're going to use Ohm's law. So if you look at it, the 2 ohm resistor is this circuit is going to look somewhat like this. You got a voltage source of 12 volts. You got a series resistance of 2 ohms. And you got 3 ohms in one branch, and you got 6 ohms in another branch. Alright? So that's another simple way to look at the circuit. So the current flowing in this would be 12. So this is going to be the main current. Right, so I'm going to denote this in blue. You have main current flowing here. So your main current I is going to be 12 volts. And I have 2 ohms in series with a branch of 3 and 6. So that's going to be 2 plus 3 parallel 6. That is 12 divided by, well, if you have 3 ohms and 6 ohms in parallel, that would be 6 into 3 by 6 plus 3. So that would give you 6 times 3 is 18 divided by 6 plus 3 is 9. So that would give you another 2 ohms. So your main current through this circuit would be 12 divided by 4, which is 3 amperes. All right. So now you need to find what is the circuit that branches off into this branch. So that current is going to be a short circuit current. So that current is going to be, using the current divider rule, I have 3 amperes times the resistance in the other branch is 6 ohms divided by resistance in both the branches is 6 plus 3. So that is known as the current divider rule. So if you have a current branching out into 2 branches, the current in your branch is calculated by the main current times the resistance in the other branch divided by the total resistance. So you would get, once again, 6 times 3 by 6 plus 3, that would be 2 amperes. So 2 amperes is your Norton's current, right, which is the same as your short circuit current. All right, guys. So in our Norton circuit conversion, we found a Norton's current to be 2 amperes. All right, so let's go ahead and now find the equivalent resistance. So the equivalent finding the protocol for finding equivalent resistance is the same way you would do it for finding a Thevenin's resistance. So I would unhook my load resistor and I would try to find what is the resistance between these 2 terminals. Equivalent resistance. And since we have a voltage source here, if you remember the rule that if you have a voltage source, you short it. And if you have a current source, you break the circuit. All right. So here, what I would go is, because I have a 12 volt voltage source, I would go ahead and I would short this. So now if I look at it, I have current. Let me denote it. So this is the main current. It would flow. And I have one current branching off, going here. And I would have another current that would branch off. They would meet back here. I'm just using these colors to make it simpler to understand. All right. So these resistors are in branches. So if you drew the equivalent circuit for it, you would have your 3 ohm resistor, just follow the blue line, and you would have the current going through the 2 ohm resistor shown in the red, and you would have your current going through the 6 ohm resistor. So the equivalent resistance, or Norton's resistance, is equal to 3 plus 2 parallel 6. That is going to be 3 plus 2 into 6 by 2 plus 6. 2 into 6 is 12. 12 by 8 is 1.5. So you would have 4.5 ohms. So that is your Norton's equivalent resistance. So I have my Norton's current, I have my Norton's equivalent resistance. Let me go ahead and erase this. Right? So using these two, I can construct finally my Norton circuit, which is going to have a current and a resistance. And I can finally hook up my load right here. So my load resistance, if you remember, was 1.5 ohms. My Norton's equivalent resistance is 4.5 ohms. And my Norton's current is 2 amperes. Okay, guys. So now if I want to know what's the current flowing through my load, I can go ahead, use Ohm's law, and I would use the current divider rule. So I would get my load current would be resistance in the other, my main current, 2 amperes, times resistance in the other branch, which is 4.5 ohms, divided by the total resistance in the both branches. So that is 4.5 and 1.5 ohms. So that would be 9 divided by 6. That is again 3 by 2. I would get 1.5 amperes. So now if I hooked up my load, I mean, I've already got my load, which has a 1.5 ohms resistance. If I hook it up, I can tell I got a current of 1.5 amperes flowing through here. So that now you know that using your Nortons so now you know that using Norton's theorems and Thevenin's theorem is pretty much interchangeable. Thank you for watching.